Okay, good morning, everyone. A little bit of orientation, A6 for the undergrads, and the grad students, hopefully you've started in on the differentiable physics assignments, D1 through D5. All good with that? So far, so good? Going once, going twice. Okay. All right. What's on tap for today? We are going to finish up Lecture 10, our discussion of active categorical perception, which will also finish up our third theme on the admittedly brief history of evolutionary robotics. And we will move on in the fourth segment here to another topic which is at the core, is at the heart of every roboticist and every robot, which is movement. What does movement have to do with intelligence, poetry, art, chess, mathematics? What's the connection? Why does movement undergird our ability to exhibit intelligent action? We will explore that in lectures 11 and 12. But before that, back to lecture 10 and active categorical perception. Just as a reminder of where we were looking at a robot that is not necessarily minimal, it's rather physiologically complex. Just to remind you of the task, like in the minimal cognition experiments, we're going to have a population of C-ternns. We're going to drop each C-ternn into the population into this robot a grand total of 16 times. 8 times where it starts in this position, and we put these 8 quote-unquote objects underneath it. There's really only 2 objects. And the 9th through 16th trial of a given C-tern, we start the robot in position B, and again put these objects underneath. And as we'll see when we get to the evolutionary part, we're going to score each C-tern for how well it allows the robot to do active categorical perception. How can it manipulate these objects and be able to perform a classification task? Determine whether it's in the presence of a sphere or an ellipsoid. Okay. We ended last time by looking at the visual representation of the C-tern controlling this robot. 22 sensor neurons, a handful of hidden neurons, a bunch of motor neurons, and then the special neurons, 47 and 48. What we're going to do, what the evolutionary algorithm is going to do, is use the values arriving at 47 and 48 to compute the fitness of that C-tern. How well is it enabling the robot to do at actively categorizing or distinguishing between spheres and ellipsoids? We ended last time with the observation that the easiest way to do this would be to sort of, quote unquote, assign neuron 47 to spheres and assign neuron 48 to ellipsoids, and decide that if the value of 47 is larger than the value of 48, or if the value of 47 is close to 1 and the value of 48 is close to 0, that's the robot telling us it's a sphere. Alternatively, if 48 was greater than 47, that would be the robot telling us it's an ellipsoid. I'm in the presence of an ellipsoid. Simple, but everything simple in life comes with a hidden cost. The hidden cost here would be if we then wanted the robot to categorize or distinguish between cubes, cones, trapezoids, rhombi, and so on, we'd have to keep adding more neurons, more synapse going into it, which means to run the C-tern, we're going to need more GPUs, more carbon, more compute, more electricity, more. Okay, depending on your point of view, more is not necessarily better. Can we do something more intelligent? Can we interpret the values of 47 and 48 differently so that the robot can still tell us whether or not it's in the presence of an ellipsoid or a sphere? But if we were then to redo the whole experiment and expose the robot to 3 different shapes, we wouldn't have to expand the cognitive architecture. We could pack more understanding into a brain of the same size. That's the game that we're playing in this particular experiment. Okay, I started last time by showing you how the investigators are going to do this. And we did that by drawing the phase diagram for the values of neurons 47 and 48. What's a phase diagram? Well, if we take the value of neuron 47 and 48 at the beginning of a simulation, and then at the next time step, and the next time step, and the next time step, we draw a trajectory in phase space. Let's imagine that we have just placed a sphere underneath the robot's hand. The robot is armed with a random CTRN. It performs some random motion, and that causes the values of 47 and 48 to change like this in the presence of a sphere. We reset the robot's arm to position A. We reset the CTRN. We zero out all the values. We pull out a sphere and put in an ellipsoid, and the robot starts moving again as dictated by the random CTRN, and it does something similarly, but then it does something differently in the presence of the ellipsoid. Okay. Are you starting to build up an intuition for how we might then apply a fitness function to these values, such that we could start evolving populations of CTRNs that if they get larger values of whatever function we derive from this, that's the CTRN allowing the robot to distinguish better from spheres and ellipsoids? Intuitions, ideas.
Would you be doing some sort of like pattern matching to what the graph is drawing for like a graph in this shape being spheres and a graph in this shape being ellipsoids? And I'm sure you get like a little bit of difference between them as different aspects of it change, but would they look relatively similar as your
Difference. Difference is the operative word here, right? Often it's useful to think about what is the worst possible thing a CTRN could cause the robot to do. What is the worst thing the robot could do that would be reported by 47 and 48? If that was the values of 47 and 48 when in the presence of an ellipsoid, it doesn't look from these neurons like the robot is feeling any difference in the presence of the sphere and the ellipsoid, right? That's the worst thing we can do. So conversely, the best thing we can do is try and get these trajectories to separate, right? To be as different as possible. Remember that one of the components of active categorical perception is magnifying inter-category differences. These objects, the geometry of these objects was chosen deliberately, so the geometry is quite simple. If the robot just put the flat of its hand on top and just moved its arm a little bit, you'd probably get something that looks like this. It wouldn't be magnifying the difference, the subtle geometric differences between these two objects. Okay. Remember, though, that for every CTRN, question? In the present, remember that we're evaluating every CTRN 16 times. So we've got one set of values for 47 and 48 during the first presentation of the sphere. Let's say we get these sets of values for neurons 47 and 48 in the first presentation of the ellipsoid. When we put the sphere underneath again, we probably get something that looks quite similar because the sphere is the sphere. We place the rotated ellipsoid under the robot's palm the next time, and it does something like this, and so on. This is the 8th presentation of the sphere, and let's imagine that this is what 47 and 48 do in the 8th presentation of the ellipsoid. Okay. Before we go on to the math, let's do a little bit of intuition. So what the investigators decided the simplest thing to do would be is to make these sets of trajectories be as far away from these sets of trajectories as possible. They did that by drawing a bounding box around all 8 trajectories produced by the 8 presentations of the sphere, and this set of this bounding box around all the presentations of the ellipsoid. So let's call this big bounding box S, and this big bounding box, sorry I didn't draw this very well, this big bounding box ellipsoid. How is the robot doing in this case? is it possible if we start to evolve populations of CTRNNs and we assign a value, a single floating point number to each CTRNN, which is the distance between these boxes, is that going to work? Can we push these boxes apart?
You probably want to try to push it apart because that overlap there is going to, say something stays only in that overlap, that's going to create some ambiguity.
Let's talk about this overlap here. Let's imagine we take an object and we place it underneath the robot's arm, and the robot exhibits a trajectory that looks like this. What is the robot telling us? What are neurons 47 and 48 telling us? What is this particular CTRNN telling us? What does the robot think this thing is? It could go either way. I don't know. It's either a sphere or an ellipsoid. What if there's a trajectory that goes here? Now what is the robot telling us? It's neither, right? I don't know what this thing is, but I'm pretty sure it's not a sphere and it's not an ellipsoid. Okay. I think this is enough intuition for now. Let's have a look at the actual math. So they're going to define a little bit of notation first. We're going to define each trial E. So remember there are 16 trials for each CTRNN. The agent is going to represent the experienced object, the one underneath, either sphere S or ellipsoid D, by associating it to a rectangle R sub E. So R sub S sub E. I'm not a fan of this notation, but we're stuck with it. So this is the E'th sphere. This is the E'th ellipsoid. And R sub S sub C is the rectangle that they're going to put around. This has gotten too messy. Let me draw it again. They're going to put an individual bounding box around each individual trajectory. So let's take the first presentation of the sphere, S1. This would be the bounding box. This would be R sub S sub 1. Yeah? So they're going to create 16 bounding boxes for each CTRNN they're evaluating in the population. The vertices of these bounding boxes are the minimum X and the minimum X and the maximum X and the minimum Y and the maximum Y of this trajectory. Here's how they write it mathematically. So here's neuron 47 and 48. We're going to parameterize it with T. They're looking at the value of 47 and 48 at 47, 0 would be the value of neuron 47 at time step 0. 47, 1 would be the value of 47 at the second time step, and so on. And then they've got this construct here. We've seen this already. What is this? Short-term memory is an important building block of intelligence. You need to rely on it. You've seen this recently. What's this? This is the value of the 47th neuron. Anybody remember? Fitz?
The activation function and the bias.
This is the activation function and the bias. It's a little confusing because when we saw the bias before, it was omega. Now it's beta. Again, a little bit of notational laziness on the point of view on the author's part here. Remember that in a CTRNN, we have the raw value of 47 and 48, which is inside the neuron. That's Y sub 47. But when we, from outside the neuron, go to read out the value, when we extract the value out of the neuron, we pull it through this function. We add the bias, and then we take an activation function, which usually caps the value or squashes the value of the neuron to -1 through +1, and same thing for this, the value of this neuron here. Yeah. So we're taking the value, these are the values of 47 and 48. We're going to look at those values across a particular time range. When I drew this trajectory here, this trajectory is meant to represent the entire length of the simulation that CTRNN is controlling the robot during the E'th trial. In this case, we're going to index lowercase t. We're going to look at the values of t between 0.95 uppercase t through uppercase t, which is not defined. Uppercase t is not defined here. Uppercase t usually refers to the last time step. 0 is the first, uppercase t is the last time step. So we're looking actually at the value, we're only looking at the last 5% of the trajectory when we create this bounding box. Why this additional detail? Why only look at the values of the trajectory during the last 5% of the simulation?
Because that's sort of when it's like made its final decision.
In the first few time steps, it doesn't matter what we place the robot in the presence of, the trajectories by definition are going to be all clustered together. The robot can't know in the very first time step what the object is because it hasn't even moved yet. Remember the active part of active categorical perception. The robot is blind. It has to move in such a way to generate sensory values, sensory repercussions that allow it to tell what's going on. So they're giving the robot time. They're giving it a lot of time. The first 95% of the simulation, the robot can do whatever it wants to do. But the goal, from the point of view of the evolutionary process, is to get these bounding boxes to be as separated as possible. So this now is RS sub 1. We can create another bounding box for R sub S sub 2, and so on. So far, so good? Have I lost anyone? Okay, all right. They are then going to compute the sphere category, the C in active categorical perception, which they're going to refer to as C sub S. This is going to correspond to the minimum bounding box around all the R sub S's. So I only have 2 on the board at the moment. So this overall category is the bounding box around all of these bounding boxes. They're putting a net around all of the final little bits of experience of the robot in these 8 cases. Okay. So that's now C sub S. We're going to have a whole bunch of other little bounding boxes for R sub D sub 1, the first presentation of the ellipsoid, second presentation of the ellipsoid, and then C sub D is the bounding box around those bounding boxes. This is what we get at the end of the 16 trials of a single CTRNN. What's the fitness function? The fitness function is going to be a function of these 2 rectangles. The hard work's done. What's left?
Test it to see how it does it, categorizing each of those rectangles.
What does it mean to categorize each of these rectangles?
Spheres or ellipsoids it hasn't seen yet.
We could put it in the presence of spheres and ellipsoids it hasn't seen after we've evolved the CTRNNs, but we're still looking for a fitness function. We haven't run evolution yet.
I was thinking you could do something like a support vector machine where you'd want to essentially maximize the distance between the categories to account for like ambiguity.
Good idea. So we could create a fitness function that tries to maximize this distance, as we were mentioning before. Push these bounding boxes apart. That's not what the investigators ended up doing.
Maybe make the bounding boxes smaller.
Ah, the size of the bounding box. We can put whatever we want in the fitness function, right? We could create a fitness function that tries to maximize the distance between the bounding boxes and makes them smaller. Why might we want to make the bounding boxes smaller?
So that they're like more accurate or
Accurate, how so? Given what we're trying to get the robot to do. It's a good intuition. Why might we want to make the bounding boxes small? This is where things get a little tricky.
Trying to like minimize the difference in the graph it's making when it detects a sphere versus an ellipsoid.
Minimize the size. That, if we did that, we would be explicitly evolving CTRNNs to reduce within category differences, which is what we want. If a CTRNN were to minimize the size of these boxes, that would mean that whenever we gave it ellipsoids rotated at different angles underneath the palm of the robot, at the end, whatever the robot was doing, all of these objects would feel, all the ellipsoids would quote unquote feel almost identical. Everybody see that? Okay. Let's just imagine we did this. There's a little bit of a problem with this though. This is where things start to get tricky. Somebody mentioned what would happen then if we brought in an ellipsoid, the same ellipsoid, but we put it underneath the palm of an evolved CTRNN that had evolved to minimize these bounding boxes. But that ellipsoid was at an angle, we rotated it at an angle underneath the robot's palm that it had never felt before. What's the problem? We're now going to start at the origin. The robot's going to use this evolved CTRNN. We've placed it in the presence of an ellipsoid, rotated at an angle it's never felt before. It's too specific. It's got to hit the bullseye, right? Remember that this is ellipsoid and this is sphere. In the presence of that quote-unquote unseen ellipsoid, the trajectory has to end up in this box at the end. If it misses it, the robot says, I don't know what that is, right? So good intuition, we're trying to reduce within category differences, but that kind of makes things problematic for generalization. We probably want this robot to be able to distinguish between spheres and ellipsoids no matter how we rotate those ellipsoids underneath the robot's palm. Tricky, right? It's kind of a simple task, distinguish between spheres and ellipsoids, but there's already subtle trade-offs that we or the robot is going to have to strike in trying to do active categorical perception correctly. Okay, apologies. That's a lot of lead up to the actual fitness function, FF, terrible notation, but we'll go with it. It's not F times F. This is just the fitness function equals two terms, F1 and F2, and we're going to try and maximize these two terms. We want FF to be very large, so we want F1 and F2 to be as large as possible. Let's start with term F1. Let's go up to the inside here, and we'll work our way back out. Let's start with dE over d max. d sub e is the Euclidean distance between the object and the center of the palm at the end of the trial, when we get here. That's d sub e, and we're going to divide d sub e by d sub max, which is the maximum distance between the palm and the object when located on the table. This is at least my d sub max. I can't go much further. We're then taking 1 minus that, which is a reminder that we're trying to minimize this. If we can drive this as close to 0 as possible, 1 minus 0 is going to be 1. And we're going to take the average of all of those values over the 16 trials. Uppercase E is the number of evaluations or trials. What is F1 during evolution rewarding CTRNNs for causing the robot to do? What actions would the robot perform that would give you a large F1, and what actions would give an F1 close to 0?
If it's made a determination, it's had more time to stand farther away, so it's going to maximize that if it's faster deciding.
Okay, there's no deciding yet. You've probably guessed the deciding is over here in F2. Forget deciding and bounding boxes for the moment. Imagine we just evolve C tier and Ns against F1, no F2. What are actions what actions would evolve that would maximize F1?
The robot actually touching the object.
Right? So if a C tier and N caused the robot to do this every time we started the robot in the presence of the object, that would give us dE would equal d max. D max over d max is 1. 1 minus 1 is 0. Worst possible thing you can do. The best possible thing is to get the numerator to be as close to 0 as possible. Minimize the distance between the palm and the object. Why is this term in here? Why aren't we just doing something with CS and CD, which we will do in F2?
I'm guessing it's like just to go off of something at the start, like to just make sure the robot's actually like touching the, you know what I mean?
Do something at the start
something at the
before
start.
you tackle this thing. We've heard that intuition several times in this class by now. What is that intuition called? Scaffolding, right? So here's scaffolding again. Remember that the robot, when we start evolution, we're dropping random C tier and Ns into the robot, which means the robot is moving this arm randomly. Here's position A. We're always starting it by touching the object, and it starts moving. The vast majority of the actions that it can perform won't even allow it to tell the difference between the sphere and the ellipsoid. So the investigators are giving the robot or giving the C tier and Ns a very strong hint on how to get started on the problem. You take a kid who doesn't know how to ride a bicycle and you put them on a bicycle without training wheels, crash, 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 crash. They're not finding a hill to start to climb, a learning curve. They're not getting sensor motor experiences that said, this worked a little bit better, this worked a little bit worse. It's just terrible, 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 terrible. Same thing here. That's why we put training wheels on bicycles, and that's why the investigators built F1 into their fitness function. Scaffolding exists across AI and robotics. Whatever it is we want an AI or robot to do, it's usually difficult from the point of view of the learner, the robot or the AI, that has little to no experience with whatever we want it to do. Terrible, 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 terrible. So we often build in a scaffold, or in this case, a scaffolding term, to get it started. Okay, so now let's start running an evolutionary algorithm in our heads. We've got a population of C tier and Ns. They start evolving, and over time, the C tier and Ns in that evolving population start to achieve higher values of F1. They keep their palm on the object. Okay, now we can start to tackle F2. Let's assume in these early generations, most of the robots are doing a terrible job at active categorical perception. All 16 trajectories are very similar. The robot is not, the random C tier and Ns or these early C tier and Ns are not magnifying between category differences. So F2 is going to start to exert evolutionary pressure on the evolving population of C tier and Ns to get better at ACP. Okay. How are they going to do that? Again, let's break down F2 by jumping into the middle of this term and work our way from the inside out. Okay. The very inside here we have C sub S and the intersection of C sub S with C sub D. Forget about all the rest of this for now. It's on the right-hand side of the minus side, which tells us we're trying to maximize overlap, minimize overlap. What do we want here? Minimize overlap. They're not actually, in this fitness function, they don't actually reward for maximizing the distance between the bounding boxes. They just want these bounding boxes to not overlap. kind of a subtle point. That probably doesn't matter too much. You could probably also go with this. They went with minimizing overlap. Tell me about the fraction here. What are they doing? Why not just take 1 minus the overlap between CS and CD? Why do this additional mathematical work with the overlap before subtracting it from 1?
It makes the overlap relative to the size of the bounding boxes you started with.
Okay, exactly. That's what the math does. Why? Why do they want to do that?
It'll have a bigger impact if it's already really localized and has a really small bounding box versus if you're very
A very small bounding box. So here are two bounding boxes, C sub S, let's say, and C sub D, that have very little overlap. Just this term says, great, you're doing a good job, but we already talked about the problem with this. So it's a little bit of math subtlety here. They're implicitly penalizing for super small bounding boxes. The easiest way to minimize overlap between two boxes is make one of them really, really, really small, and we already talked about what the problem is with that. So they're normalizing the amount of overlap by the minimum of the area of the smallest one. So they're going to evolve CTR and Ns to minimize the overlap, hopefully get it close to 0, without also evolving smaller and smaller bounding boxes. Everybody see that? Okay. So according to F2, this is terrible. This is terrible. Something like this and this box, pretty good. That would give us something very close to 0. 1 minus 0 is very good. If F1 is greater than or equal to 1. So this is something we haven't seen before. This is a conditional fitness function. Basically what this is saying is the evolutionary process is telling the CTR and Ns, get better at F1. Figure out F1 first. And as F1 starts to rise, if a CTR and N in the evolving population starts to achieve a value of F1 equal to 1, great. You figured out how to ride a bicycle with the training wheels, and now we're going to give you additional points. You're going to suddenly start to get values of greater than 0 for F2. Now that you know how to keep your palm on the object, are we going to start to see how well you can distinguish between spheres and ellipsoids? This is all ridiculously more complicated than saying 47 is greater than 48. That means sphere. So we're doing a lot of extra work here, but we've already hopefully motivated for you the reason why we're doing this. I'll show you the results of the experiment with spheres and ellipsoids in a moment. What if we had spheres, ellipsoids, and cones? What do we do now? Let's imagine we have C sub S for spheres, C sub D for ellipsoids, and C sub C, sorry, terrible notation, for cones. What do we need to change in the experiment?
Try to minimize the union of all three of them.
The only thing we would have to change, well, I guess we'd have to start presenting cones underneath the robot's palm also, but all the other machinery, the CTR and N, calculating bounding boxes and all the rest, adding sensors and motors or joints, we don't have to change anything else except the fitness function, right? This is the elegance of robotics. If we set things up correctly, we want to get the robot to do more complicated versions of what it was able to do before. Just change how we reward and punish evolving brains in this case. So we would do something like look at the pairwise overlap of all three. The overlap between S and C, S and D and C, and normalize them so that we make sure that we don't evolve very small bounding boxes. And hopefully we would end up with something that looks more or less like this. C sub S, C sub D, C sub C. The robot would magnify, or we would evolve C tier and Ns that magnify intercategory differences. Yep. And on and on and on. We could add a fourth object, fifth, sixth, 10th, 100th. Okay. All right. Let's see what the robot actually does. We're going to look at an evolved C tier and N. Just as a reminder, you're going to see 16 presentations, or 16 trials, 8 in position A, 8 in position B. I'll turn off the light so you can see this a little bit better. Here we go. Oops, sorry. Can you see the little blue arrow between sphere and ellipsoid? A little hard to see. Here's an evolved C tier and N. This is one C tier and N that has a high value of F1 and F2. Is it magnifying intercategory differences? Is it minimizing intra-category differences? When they constructed this video, how did they figure out how to draw the blue arrow? They're running one evolved C tier and N in the simulated robot's arm, and they're showing us what the robot thinks about the object that it's in contact with.
Are they taking which of the bounding boxes the point ends in and having the arrow point at that?
Absolutely. So when they start, the trajectory does this, and the blue arrow is vertical. The robot doesn't know that what it's in the presence of. And then eventually, the trajectory wanders into one of these bounding boxes, and at that point, they draw the blue arrow pointing to whatever that category is. That's the robot, quote unquote, telling us what it thinks it's in the presence of. Okay, same evolved C tier and N, but now you're going to see the 9th through 16th trials. Note how its grasp and movement is different in the presence of the sphere or the ellipsoid. Imagine I blindfolded you and asked you to try and figure this out. Is this what you'd be doing? Okay, I'm going to turn the lights back on. I don't know about you, but it's not really so obvious, right? It's quite subtle. It's not like it's making some very obvious different sets of movements in these two cases. But it's good enough for the robot. Whatever these slight differences in actions are, they're magnifying the values of 47 and 48. So as we watch the robot, actions look similar, but quote unquote, in the mind of the robot, it quote unquote feels, these different objects feel quite different. Okay, we've spent a fair bit of time on this lecture, so I want to finish up, but I want to just do one last thought experiment with the ACP robot before we move on to legged locomotion. These objects, they also have a certain semantic distance between them. For humans. If I tell you about spheres, ellipsoids, and cubes, one of these three objects doesn't belong. Which one? Spheres, ellipsoids, and cubes. Don't think about it, just react. Which one? We should all be in agreement. Cubes, right? Why? What's so different about cubes?
Cubes have sides and corners.
Sides and corners, you're giving me a geometric description. That's obviously why they're so different. You can't roll them. There we go. There's an affordance type answer, right? There's something about when we grab it, we feel the edges and the pointy parts more than we do when we grab spheres and ellipsoids. Why does that matter? Well, in AI, we often talk about alignment. We want intelligent machines to feel or experience the world similarly to humans, so that when they make value judgments, they tend to make value judgments in the way that a human would if the human were in that situation. How could we take, if we were redoing this experiment with spheres, ellipsoids, and cubes, how might you alter the fitness function now to help align the robot with us? We want cubes to feel more different to this robot than spheres and ellipsoids do. What might you alter about, let me go back to the fitness function for a moment. What might you alter about the fitness function so that the C-ternons that evolve are more aligned with us? They cause the robot to feel cubes as more different than spheres and ellipsoids. Ideas? Remember, we've got the three bounding boxes, CS, CD, and CC.
You would want CS and CD to be closer together and CC to be something farther away.
We still don't want CS and CD, exactly. We don't want CS and CD to overlap, but now we might start to bring in distance. They should not overlap, but they should be closer to each other than C sub C. That could be some math that we build into the fitness function, and that's us telling the robot, this is how spheres, ellipsoids, and cubes feel to us humans. Evolve such that they feel also like that to you. We want you to be aligned with us. Okay. For those of you that have taken an AI course and you've heard about alignment before, just connecting what we just talked about with this unsolved problem in AI. Okay, we got half an hour left, so we can now switch gears, no pun intended, from the history of evolutionary robotics to locomotion. And we're going to start with legged locomotion. I told you about Linus's rhetorical question about why don't plants have brains. According to Linus, who's a neuroscientist, they don't have brains because plants don't have to move. In neuroscience, the brain is often referred to as a prediction machine. Whenever roboticists hear that, we always push back. Again, no pun intended. Brains are movement machines. Or at least they started as movement machines from the beginning, and they built prediction, prospection, active categorical perception, self-non-self discrimination, all the other building blocks we've seen so far, and hundreds or thousands more on top of this. With that simple movement, most of my visual information has now almost completely changed. I'm lost. What happened? The moment I move, how can I make sense of what's happened? That's number one. So in lecture 11, we're going to start by looking at a whole bunch of different animals, and we're going to look at how Mother Nature solved the movement problem in animals, mostly using brains, not exclusively, but mostly using brains, and then try and take the intuitions we build up from biomechanics, how animals and humans move, and how do we build that into robots that use their C-ternons or use their neural network controllers to orchestrate movement first, and then start to layer on top of that the other building blocks of intelligence. Okay, here we go. Before we do that, we should acknowledge the state of the art in robotics when it comes to locomotion. There's lots of cool robot videos out there these days. Anybody know which one this one is?
Is that the Boston Dynamics one?
Not the Boston Dynamics one. The Boston Dynamics one is the ancestor of this one. It's not Boeing. Boeing wishes they could do this. Not quite yet.
China?
This is a Chinese company called Unitree. This is A2. There's G2. Not bad. I think it's safe to say at this point in robotics, the locomotion has been solved. We can clearly get machines that locomote arguably as well as any human or animal on the planet. Not bad. Okay.
I've seen ones with a similar build that have wheels for like feet,
Ah.
while also having.
The same company, with this robot, you can put wheels on the bottom and you get what's called WEGs, combined wheels and legs. We'll see a WEGed robot later in the course. You just saw an adult human stand on the back of this robot. Not too bad.
Would you say China is leading the world in robotics right now? Because at least I keep seeing robots coming out of China that are just way more advanced than anything I've ever seen.
They certainly got cooler videos at the moment, right? Remember, this is also a promotional video, although at this point it's kind of hard to fake this level of performance. Now, what would you want a robot like this for? Here's maybe a demonstration. Seems like a bit of overkill, but maybe not. I think we're on the verge of these things actually being useful to people in everyday settings. Not quite, but we're almost there. Given what you know about legged locomotion, you are one. How is this robot building on, what is it sort of borrowing from nature? It's borrowing thousands of things from nature, some more obvious than others from this video. Four legs. A lot of four-legged animals out there. Pretty good, right? 3 is okay, but not great. 6 is also very successful, but you see mostly 6 legs at the very small scale in nature. 4 seems to be pretty good. 2 is also good, but it's got its drawbacks, as we all know. Or you will know when you're 51 years old and you have lower back problems. Problems with bipedal locomotion. What else?
It's got the same leg shape as like a lot of dogs' back legs, but for all 4.
Exactly. So they've kind of borrowed some things, and other things they're kind of moving around, right? Backward pointing knees is a good solution. Turns out it also works for forward legs. You don't see it so much in nature, but there you go. If you're a 4-legged animal or robot, why are knees good in the first place? Forward or backward pointing?
Helps you adjust how you're on like unlevel ground.
Absolutely. So you see this thing scrabbling over a lot of uneven ground. It helps maintain balance. It also is good at not propagating shocks back up into the main body. If I didn't have knees, I'd have much worse back problems than I do right now, right? It helps. It helps. Okay. Lots of biological inspiration here. We're not going to talk about how this robot was made. We're going to look at some earlier experiments and look at how the field has built up to this level of sophistication. What do we need to get right in order for this to happen? Okay, we'll come back to robots in a little bit, but we're going to spend a few minutes now in the animal kingdom. I'm going to show you the table of contents from this book. I love, love, love this book. I know you're all very busy people, but if you're interested in the brain as a movement machine, I highly recommend Alexander's Principles of Animal Locomotion. It's the Bible on this topic. Just from the table of contents, I hope to convince you of why this book is so awesome. The chapters, first of all, go through muscle, the main thing that produces motion in the animal kingdom, and then goes into the energetics of travel. So as we move around, the world around us changes, and moving around is an energy hog. And we have this thing, which is also an energy hog. So balancing energetics is very, very important. How big or small you are is important. The book goes through how humans have studied animal locomotion for decades. I'm going to pause for a moment. I've mentioned energy now. Somebody, when we talked about knees, said that allows you to keep your balance, stability, on uneven terrain, lots of different types of terrain. It's great if I can walk on carpets, but I'm not going to get very far if I can only walk on carpets. I'm not going to make it home tonight. It's important as something that moves around in the world that you're able to move across different terrains and different environments, and the breadth of the range of environments that you can successfully move across, that's your robustness. We're pretty good at climbing mountains, but we can't hold a candle to mountain goats, right? They can go places we cannot go, and vice versa. Not every animal can traverse on legs every environment on this planet. There's a trade-off. So there is a trade-off between how much energy you use to move, how stable you are as you move, or what's the risk of falling over as you move. And then finally, the one that's really kind of the thing you care about, which is displacement. How far can you go? Every single form of locomotion in every animal species on this planet, every individual species strikes a different trade-off between these four desiderata, these four things that you at least have to have some competency in to get around on this planet. Some double down on one of these four and kind of sacrifice some of the others. We're going to talk about us in the next lecture, bipeds, but just for the sake of argument this morning, humans evolutionarily have struck a very extreme balance here. There's one of these things that we're really, really good at and not so good at the other ones. What is it? Energy, right? We've already talked about this. Most of the time, if you're not running, most of the time you're walking, most of the time our ancestors were walking, and most of the time one of your legs is resting at all times. That makes us extremely energy efficient. We pay quite a bit of cost for this. It takes quite a bit of time to figure out how to move quickly on two legs without falling down. And for our distant ancestors, in which there were other apex predators around, this was actually quite a big cost to pay. The ability to not stay upright and move quickly when you were young, that was a huge cost. Hopefully mom or dad or other kin were around to protect you. So we got really good at this, and we've paid a cost for this. Robustness, we're actually not too bad. In robustness, we can travel across swamps, deserts, plains, mountains, kind of. Displacement, we're not so great. We don't travel very quickly. You can run, but not for very long. There's plenty of other species out there that can travel much further than us in a single day. Yeah? What are some other animals that have struck very different trade-offs? We are very energy efficient, not so good at the other ones. Lots of choices out there.
My dog can move pretty fast, cross different terrain, relatively good at not falling over, but
Yep.
he loves a good nap.
Fair enough. Dogs. Okay, let's take dogs. Pretty good. If they're properly motivated, given their size, they can travel much further in a given day than we are. They're pretty good at clambering over things, possibly better than we are. Not as energy efficient. They got 4 legs to maintain. Not half of their legs are at rest at every moment in time. They're not as energy efficient as we are. Pretty good at not falling over like us. Let's go beyond legged animals. Legs are great, but there's lots of other options out there. What are some other very extreme trade-offs?
Snakes.
Snakes, good. All right, love snakes. What are snakes really good at and really not good at? Slithering. They're very good at slithering. What does slithering do to these 4 desiderata? I invite you in the privacy of your own home to get down on your belly and give this a try. What happens? First of all, we're not good at it, but you can do it. What's the problem?
It's like kind of impossible to fall over from slithering, I would say.
That's what slithering is for. And never got to worry about falling over. Tree snakes, different matter, but there are many, many animals on this species that have chosen to stay low to the ground. You're all laughing, that's fine. This doesn't stay close to the ground, but possibly if we want to have a lot of fast-moving autonomous machines around, we might want them to be actually closer to snakes. They're not big, heavy machines that from time to time fall over. That's maybe not so great to have those things near humans. Maybe we do want to create machines that strike balances that are closer to slithering than walking. Walking looks cool and produces slick promotional videos for the corporations that produce them, but again, in the grander ambition of trying to create safe and autonomous machines, low to the ground is actually a pretty safe way to go. So I invite you as budding roboticists to not be anthrochauvinists. Don't build robots like us because obviously we are the best way to do it. That is mathematically false. There is no best way. There's just different trade-offs that can be struck, and different species strike different trade-offs given their ecological niche and how they try and find mates and eat and so on. We also need to think about machines and how we want to evolve or train them or design them to strike different balances as they move around in the real world with us.
For locomotion methods that are, biologically impossible, let's say, I know I mentioned wheels on legs.
Yes.
Is that something to consider? Is that robots would look nothing like what we've seen on Earth?
It's a great question. So you mentioned biological impossibility, right? There's no animals out there with wheels. It's actually an open question. It's not necessarily impossible for Mother Nature. It may be that she just didn't find that solution, or that solution wasn't appropriate for the environments in which she started to find the rudiments. No roads. There are very large, flat expanses of land out there. So arguably, there are niches in which wheels might have been useful. It's complicated. Doesn't mean it's impossible for Mother Nature. It might be that she just didn't choose it in the right place at the right time. Okay, back to your second point is maybe we build robots that don't look or move like any species on Earth, and that allows them to strike a unique trade-off between these four desiderata, and that's a good thing for us. That ends up producing safe and autonomous machines. I'd say nobody knows. Maybe yes. Maybe this really is the answer to safe and autonomous machines, or maybe the body plans of safe and autonomous machines are going to look very, very different. I don't think anybody knows yet. Okay, the important thing I want you to take away from this slide and lecture 11 is this, these four desiderata: displacement, robustness, energy, and stability. Okay, all right, back to the book. Chapter 6 and onward starts to go through all the different ways that Mother Nature has discovered movement for animals. Crawling, peristalsis, hopping, so we mentioned slithering already. Peristalsis, one of the earliest forms of locomotion discovered, actually in the oceans and then again on land. If you're a one-dimensional creature, you're basically a line. If you expand one part of your line and then you contract that part of your line, contract the part just below it, contract that part, and you create a moving wave of expansion moving from your head to your tail that produces forward motion. Earthworms do it, lots of other creatures do it. You also do it, but you don't do it to move. You peristalt. Where?
Swimming?
Not outside your body. You can do it kind of with swimming. Swimming is still kind of slithering.
You're like intestines and entire digestive system.
The entire digestive system, right? When you finish up here and you go have your blueberry muffin, you take a bite, your trachea will peristalt, and then your intestine and will push the food all the way to its final destination, right? Mother Nature discovered movement very early on, and then she exapted it. She exapted it for other purposes. Exaptation is a phenomenon in evolutionary systems, which is Mother Nature is many things. She's also lazy. She tends not to reinvent things from scratch. She finds things that were adaptive before, and she exploits them for new purposes. Peristalsis was worked out very, very early on in the animal lineage, and it turns out it's useful not just for moving the animal, but also moving stuff, like blueberry muffins, inside animals. Okay, exaptation will come up again later in the course. Okay, chapter 7, this is kind of where we hang out. No pun intended. Walking, running, and hopping, climbing and jumping. I love, love, love brachiation. We've already seen a brachiating robot. Beautiful form of locomotion. For this niche, moving through a canopy, it's actually energy efficient. If you've ever done it, it certainly doesn't feel like it's energy efficient. It's super hard, but given the alternatives, climbing carefully from limb to limb, actually you end up expending much more energy. Okay, crawling and burrowing, we just talked about that. Gliding and soaring, we're terrible at this unless we build huge metal birds and fly them through the air. Hovering, we're also terrible at. Powered forward flight, we can't do any of these things. It took us a long time to build machines that we can then sit inside that do these things. Moving on the surface of water, also we're not so good at it. Swimming with oars and hydrofoils, swimming by undulation, swimming by jet propulsion. Buoyancy, aids to human locomotion machines. I love, love, love this book. I could talk about it all day. I'll shut up about this book. Okay. We've already mentioned slithering, and the advantage of slithering is you never fall over, but again, remember there's always a trade-off. So snakes and reptiles stay very close to the ground. They stay on the ground, but they pay a heavy cost for that stability, which is they're literally dragging themselves across the ground, and that friction absorbs energy, saps the animal of energy that's dispersed as heat. So not great. Okay. All right, so we're going to look at some other animals again and look at specific trade-offs that are struck. And we're going to talk a little bit about how the data that we're going to look at was collected. In biomechanics, they need to be able to measure how fast an animal is using and how much energy it's burning as it moves. Some of you may actually have done this test. If you're a high-performance athlete, you've done max CO2 before. If it's an animal like us that's willing to wear a mask, you put a mask on. If it's an animal that's not very happy wearing masks, you put them in a little a sealed cage. Put them on a treadmill, turn up the treadmill, turn down the treadmill. You force the animal or the human to move at a certain speed. And then you measure the rate at which oxygen is turned into carbon dioxide. The faster or the more oxygen that's turned into more carbon dioxide, the more energy the animal is using at that time, more or less. It's approximate, but it's a pretty good proxy for the actual amount of energy you're using. Okay, there's lots of super fun experiments you can do given this, and then you start to get back some data. So let's have a look at humans, specifically male humans, that are walking and running. So on the horizontal axis here is speed measured in meters per second. So they put adult human males wearing a CO2 mask on the treadmill and turned it up and asked them to walk or run. Good thing about humans is most of the time they will obey natural language instructions. So here's the treadmill not moving at all, being sped up to a little more than 2 meters per second, and the male being told, walk, don't run. The vertical axis is reporting one way of reporting energy expenditure, which in this case is the power used by the human in watts. What happens? What's happening?
It's exponentially increasing.
You can try this yourself. I don't recommend it. You can force yourself to walk on a treadmill and keep turning it up. You're going to start to huff and puff very quickly, and at some point you're going to fall off the end of the treadmill. It is not a straight line. There's not just a trade-off between these four desiderata that we talked about. Depending on your physiology, the way that you're built, these trade-offs become very complicated very quickly. Here's remember, walking is energy efficient at a certain point, but under different environments, like a fast-moving treadmill, it suddenly becomes not energy efficient at all. So what do most of us increasingly want to do under these circumstances is switch to our second gait, which is running. Tell me about running. Or at least for these males running on the treadmill. What happens now?
There's time where like both of your legs are unweighted.
There's a certain point in time in which both legs are unweighted.
Yeah.
Not quite. Again, this is tricky to do. When you're running, there are points in time in which both legs are off the ground. They're not both relaxed. If they do, you're going to end up in the ER when you hit the ground. You actually have to tense your legs to prepare for imminent arrival.
When you're moving one leg, you're covering more distance with it,
Oh.
so you're able to keep up, like in that scenario, you keep up with the treadmill if you're covering more distance with one movement.
Possibly. So good observations. Let's pull out of the physiological details. Just what is the chart telling us? What's it telling us about the overall relationship between speed and energy here?
It's like it's linear, so
It's-
it's more consistent at higher.
It's got a different profile. There's a different relationship between energy, speed, and displacement for different gaits. Gaits are specific to legged animals. The point I want you to take away here is, again, just how complicated it gets very quickly. You'll notice that at certain speeds, at 2 meters per second, it's better to walk. Better in the sense that to move at the same speed, you're using less energy. At, what is this, 2.2, a little bit beyond 2.2, not a good idea to walk. You know those ridiculous looking speed walkers? That's what you need to do at 2.2 meters per second. Extremely energy inefficient. That's why we all laugh when you look at a speed walker. We know that they're intentionally choosing to do the wrong thing. The basis of most comedy. Okay. Tell me about this plot here. So if you can't read it, we've got stride frequency in hertz on the horizontal axis. So 1 hertz means 1 step per second. 1.25 is 1 step every 3/4 of a second. 0.5 is 1 step every 1.25 seconds. Vertical axis, again, is power. What's happening now? These are for adult human males. What's the relationship we're looking at now?
It's actually harder to move slower, and there's an optimal place where you're moving your legs and using energy.
Absolutely. There's an optimal frequency for strides. You said slower. I think you're implying slower than the usual way we, as adult human males, tend to do things. Again, if you've got some time today, get out your phone, start up a timer so you can watch seconds flip by and count. You will find whether, even if you're a smaller human or a larger human, you tend to walk at about 1 footfall per second. Just happens to be, for human physiology, that's a good way to do things. Not exactly 1, but pretty close to 1.
Is that for a fixed, like, velocity?
Yes, sorry. 1.5 meters per second. So they put humans on the treadmill, and the treadmill is moving at 1.5 meters per second, and they had a metronome. And they told the human males, every time you hear a click of the metronome, make sure a foot falls. It takes a little bit of practice to be able to do this, but you can do it. Right? Basically walk on command.
So then for lower frequency, your stride's longer.
Exactly.
So you'd also be using, like, depending on how long it is, potentially like part of your like quad or upper leg more.
You're not always relaxing one of your legs for half the time all the time. Yep, exactly. Interestingly, your brain emits vibrations at different frequencies or oscillates at different frequencies. There are certain frequencies, if we put you in a brain scan, there are certain frequency peaks. There are certain oscillations, electrical oscillations going on in the brain at certain frequencies. One of the strongest ones, 1 hertz. And you're in a brain scan, you're not walking. Further indirect evidence that brains are movement machines, first and foremost. Okay. All right. Any question?
A little bit. Do you think that's why a second is a second?
Very good question. Yeah, where did the second come from? Good question. Possibly. Of all the explanations I've heard, I think this one is probably the best one. We all have somehow the same kind of timekeeping. The most natural beat in our heads and in our bodies is 1 hertz. Probably not a coincidence, but who knows? Who knows? Okay, any horse people here? Okay, how many gaits do horses have? 4, thank you, or 5. Definitely a horse person here. Walking, trotting, galloping, and I'm missing cantering. What's the 5th one? Most horses have 4. There's one species of horse that has a 5th one.
Pacing?
Pacing, I don't think strictly counts. It's like a version of one of these 4.
I think Icelandic ponies can do like a speed walk.
A speed walk. Tilting. Yeah, exactly. So, 4-legged animals, at least big ones, they have different gaits from us. And then within the same group, there are different species of horse that have more or less gaits. Again, things get super complicated very quickly. All right, since we've got horses up on the slide here, let's introduce some terminology which we'll use for the rest of this lecture and also for robotics moving forward. Stance phase. So if you watch an animal or a human as it's doing its thing, any given gait, you can ask at a given moment in time whether the animal is in stance phase. Stance phase meaning there is at least 1 foot on the ground, or is the animal in flight phase, no feet on the ground. When we walk, do you have a flight phase? Is there ever a moment in time in which both feet are off the ground? So walking is energy efficient and kind of helps with stability. When we run, when we fall into our second gait that we tend to use, running, there is a flight phase. I'm not going to demonstrate it here this morning, or you're going to be taking me to the ER. We alternate stance and flight phase when we're running. Interestingly, there was a person who was interested in horse gaits, and it wasn't clear from watching the horse. It's very difficult to do when you watch a horse to know whether in certain gaits there is a flight phase. Is there ever a short moment in time in which all 4 feet are off the ground? So this person got very frustrated and wanted to answer this question. So this person came up with a technology in which they could take a picture of the horse and then a very short moment in time later, take another picture of the same horse, and then another picture, and then another picture, and then another picture. And this person was flabbergasted when they put all these pictures together and flicked these pictures. Suddenly they could see the horse moving. And by the way, they were able to answer the question that yes, there is a flight phase. And they invented the motion picture camera in the process. Okay, I'll leave it to you to look into who exactly that was. Not important, not relevant for our discussion today. Okay. All right, another 4-legged animal that's already been mentioned in this class. Lots of different interesting gaits. Okay, we've got 2 minutes left, so let's just introduce some more terminology that'll be useful in our discussion about movement. Static versus dynamic stability. Remember, stability is one of our important desiderata. We want to make sure we make big, heavy, fast-moving machines that don't fall over unintentionally. It matters. What is static stability? Static stability means for a given animal or a machine, while in movement, if it stops moving, it won't fall over. When you are walking, and again, you can try this in the privacy of your own home, at any moment in time, tell yourself to stop moving, and you will generally be statically stable. When we're walking, most of our weight tends to be over our stance foot, the one that's on the ground. As we step with our other foot, we shift our center of mass over it, and most of the time, if we are to stop moving while walking, we don't fall over. So part of the advantage of human walking is static stability. Dynamic stability is a little more tricky. This is an observed pattern over time that continues, walking or running, and if we are perturbed from outside, you get hit by something or there's a sudden big gust of wind, if it knocks you over, you're not dynamically stable. There are certain ways of moving where you're kind of throwing your weight inside where you're moving so that even if you get hit, you're unlikely to be pushed outside of that oscillatory pattern. There's other ways of moving that if you get hit, you're likely to be knocked over. Again, this matters for us as roboticists. If we're going to have legged machines or wegged machines, things that are moving and exhibiting oscillations as they move, and they get hit, you want to hope that most of those unexpected hits don't disrupt the oscillation, the way that they're moving. That's dynamic stability. Okay, last piece of terminology is polygon of support. At any given moment in time, you can look at an animal and assuming it has at least one stance foot, there's at least 1 foot on the ground, you can draw on the ground what's called the polygon of support. At the moment I have 2 feet on the ground, you can draw a polygon around the outsides of my 2 feet. Now I have a polygon of support that is exactly in the shape of my left foot. As long as your center of mass is inside that polygon of support, generally speaking, you are what? Statically or dynamically stable. You're statically stable as long as you're moving slowly. If you're moving quickly and your center of mass is entering the polygon of support and is about to leave again, maybe not. But generally speaking, walking for us is quite stable because we're always keeping our center of mass between our polygon of support. Okay, we'll continue our discussion about movement on Tuesday. You have a quiz due tonight and you're working on A6 or D1. See you next week.